Hello everybody, my name is Scottie Thomas, and for our stage take-home exam, I decided to do the leaching problem. We were given three subsection concept questions that we had to answer before we got into our actual calculations. The first question asked me, how do I determine the number of equilibrium stages needed in a cascade? I decided to use the algebraic approach. In the algebraic approach, we first have to find the component k value, which we can do either graphically, which we can use figure 2.4 in the book, or we can use another method like Raoult's law, modified Raoult's law, or Henry's law. The next step is to calculate our absorbing or stripping factor, which we can calculate very easily if we know our liquid and vapor flow rates. From there, we look at our fraction absorbed or fraction stripped equation, which is found in chapter 6, and we can directly solve for n, which is the number of stages. The next thing I had to determine was what caused a pressure drop in a trade column. The three main factors that causes pressure drop in a trade column is friction from the vapor flow, holdup of the equivalent clear liquid, and the losses that occur due to surface tension in the flow. The last conceptual question that we had is what is the difference between a loading point and a flooding point in a packed column. Loading point is the upper limit of the gas velocities that will allow for the liquid to be held up uniformly. Flooding point is the gas drag force is sufficient to entrain the entire liquid. Next, I'm going to begin calculating the actual numerical problem that we were given for this assignment. First, we're going to start out with a basic overview. In our problem statement, we were told that there are three stages, and we were also told that the solution flow rate is equal to the feed flow rate. We were also given the composition of our feed stream. There are a few assumptions that I made going into this problem. I assumed that there is no solids in the overflow. I also assumed a feed rate of 100 kilograms per hour, and I also assumed that all the underflow flows remain constant throughout the entire problem. And to calculate the underflows, I used the given ratio that we were given in the problem statement. I took the amount of insoluble material and I multiplied by the ratio of ratio of solution to insoluble material, and I got a flow rate of 20 kilograms per hour, which will stay consistent throughout the entire portion. From here, I use this data to calculate and do our material balances. First thing I decided to do out of order from the problem is do our solution material balance. I calculated the material balance around each stage empirically, then I plugged in my known values, and working from stage 3 back to stage 1, I found the flow rates in our overflow. From this, I then went and did my solute material balance. We have to remember that since this problem is considered to be in equilibrium between every stage, our x component and y component for each stage is equal to one another. That means for stage 1, I put x2 v2 and x1 l1. The reason I decided to keep everything as x in this equation is because x and y are equal, so it makes it easier whenever I'm solving for the values later on in the problem. So for each stage, I created a solute material balance, and by solving all three of these equations at the same time, I'm able to see what the component values are. You can do this either with Excel, matrices, or other comparable math programs. The next phase is to figure out the kind of solubles that we have in our overflow and the percent of the inlet. I gave a quick overview again, just to remember in case we get confused. Now, for solubles in the overflow, I go to each stage and I multiply the component that will give me what the overflow range is. Next, for percent of inlet, I will go to each stage and divide the amount of solubles that we have in the overflow by our total amount of solubles, and then that gives me the percentage and percent of the inlet. And this is how you perform the leaching problem on our take-home exam. Here are my sources, and thank you for watching my video.